All right, let's get started. Good evening. Welcome to the environmental lecture presented by Pittsburgh, a local section of the American Chemical Society. My name is Rong Hong Lin, and I'm a member of the ACS Pittsburgh Local Section Executive Board and the chair of the environmental group. The environmental group is one topic group within the Pittsburgh Local Section and was formed with the aim to educate and promote awareness about our environment. We support a variety of activities. And tonight's lecture is the second of the environmental lecture series, which we plan to continue monthly throughout the year. And we intend to continue with a variety of speakers from industry, academia, as well as other research institutes, and will cover various chemistry and environmental science related topics. Just to let you know that the lecture is being recorded and will be available on YouTube. I would like to remind attendees and future viewers that the views and opinions expressed in this lecture are solely those of the presenters and do not necessarily represent the views of the ACS Pittsburgh local section. And also the mention of any specific products, services, or companies does not constitute or imply the endorsement or recommendation of such products, services, or companies by the ACS Pittsburgh local section. Now, it's my great honor to introduce tonight's speakers, my colleagues at Calgon Carbon Corporation, John Matthews and Rebecca DeStefano. John is the Director of Global Business Development and leads the PFAS Task Force. He has conducted more than 10 webinars on PFAS treatment with active carbon and has spoken at various technical conferences. John earned his double BS in chemistry and mathematics from Duquesne University, his MS in chemical engineering, and his MBA from the University of Pittsburgh. Rebecca is a senior applications engineer in the Industrial Solutions and Diversified Applications Business Unit. Prior to this position, Rebecca was a senior group leader of carbon applications and testing, overseeing testing to evaluate carbon performance for PFAS removal. Rebecca received her BS degree in chemical engineering from Penn State and her MBA from Robert Morris University in Pennsylvania. The topic tonight is effective and sustainable treatment of PFAS with granular active carbon. And we will have a Q&A at the end of the lecture, and please submit any questions using the chat window. With that, please join me and welcome our speakers, John and Rebecca.
Thanks, Rong Hong. I'm going to go ahead and take over the screen now, if that's okay.
Mm-hmm.
Okay. Okay. Can you confirm if you can see my screen?
Yes.
Okay. Very good. So thank you all for having us here today. It's a great honor to be here speaking to the ACS Pittsburgh local chapter. As my intro probably alludes to, I'm a Pittsburgh native, born and raised, and happy to be here speaking to you about activated carbon treatment for PFAS. To give you a little bit of background on the company, who we are, just because I think it's one of Pittsburgh's best secrets, so to speak. We're a company known as Calgon Carbon Corporation. We are an independent subsidiary of a large chemical company in Japan called a Karari company, but we're the world's largest manufacturer of activated carbon and provide a lot of strong R&D capabilities, a lot of specialized products for applications such as PFAS treatment, which we'll talk about here today, and really do a lot of amazing things when it comes to liquid and vapor purification. As it relates to our specific company history, we've been around since 1942. In 1942, one of the applications for activated carbon is actually military gas mask in protection. And at the time, they were sourcing a lot of activated carbon from Southeast Asia from coconut shells. And the U.S. government wanted a domestic source for military protection. So they tasked then Pittsburgh Coke and Chemical with developing activated carbon from something made from a domestic source in the United States. And just so happened that bituminous coal was the product that we ultimately found a way to make activated carbon from and haven't looked back since. We've got over $800 million in net sales annually. We have over 100 years of experience with activated carbon and activated carbon development, 1,700 employees worldwide, various manufacturing reactivation plants throughout the world, and being a part of the Harari organization really helps us to further advance the technology and further advance mankind by purifying water and purifying air. This just gives you some perspective of our footprint. We are headquartered in Pittsburgh, Pennsylvania. That is our global headquarters, but we've got various manufacturing facilities throughout the United States as well as throughout the world. You'll see when we talk about various types of activated carbon and what makes a good activated carbon for PFAS removal, that it's really a lot of the bituminous coal-based product manufactured here in the United States, but we also manufacture various activated carbons in Europe from wood, and then in Southeast Asia, we also have manufacturing assets for coconut activated carbons as well. As it relates to our portfolio, we really focus on activated carbon-based sorbents. So coal-based, wood-based, coconut-based. We also have some novel forms of activated carbon, something called carbon cloth, which is used a lot in advanced wound care healing, as well as in CBRN suit protection. We also have what's called a carbon sheet technology, which is a rather cool product used a lot for fugitive emissions from vehicles, basically adsorbing and desorbing gasoline vapors as it's purged from the tank and in use. And then we also are the world's leading reactivator of activated carbon as well. So with that, that's enough for the company overview. I'm going to turn it over to Rebecca for some PFAS introductions and a current explanation of some of the best available treatment technologies for them.
Thanks, John, and thanks for everybody for attending this, and I'm happy to be here to speak with everybody about this topic. We're going to kind of go back and forth between the different sections of the talk so that it's not one voice through the whole thing. So I'll go through this section and then hand it back to John for another section and kind of continue from there. So to get into the PFAS topic, PFAS is obviously an acronym. It stands for per and polyfluoroalkyl substances, and they're a class of chemical that's a fluorinated compound, and shown here PFOA and PFOS. So you see the black chain is a carbon, or the carbon molecules. The green molecules attached are the fluorine, and then different head groups depending on the compound. And there are so many different permutations of these that have been in development. I think the inception goes back to the 50s, but the branched version, the linear version, all the different head groups, different, as I said, permutations result in over 4,000 different compounds within this class of chemical. And you may have heard, years ago, PFCs. So all PFAS are PFCs, but not all PFCs are PFAS, is the way to kind of think about it, because we do want to see like a mostly saturated compound with fluorine. Why they're a problem? They're very persistent. They're obviously man-made. They're not naturally occurring compounds, and they don't break down. They hang around the environment. They're persistent within the environment and within the human body when you come in contact with contaminated food or beverages. Where they've come from and why they are so prevalent was they've been used in anything that basically stain resistant, non-stick. So in your home, out in the environment, they're finding them on ski slopes because they're used in the wax that's used on skis. Another product that dispersed them widely was called AFFF. So I'm forgetting what the A stands for, but aqueous film forming foam that is really, really good at putting out fuel fires. So used a lot of times at Air Force bases, military bases for hydrocarbon fires that you can't put out with water. They would spray this foam, immediately blankets it, excludes oxygen, and then the fire's out. So from a safety perspective, they were excellent for that function. Unfortunately, again, they don't break down, so that allowed them to then run off in different points and then eventually be contaminating groundwater. So, so the next slide will show a little bit of a close-up on the PFOA and the PFOS molecules. So again, you see the carbon chains and then the fluorine atoms bound on that chain, fully saturating it. So PFOA is perfluorooctanoic acid with the carboxylic acid head. PFOS is perfluorooctane sulfonic acid with a sulfonic head group. And different head groups just impart different properties, and they're used for different applications within those types of products. So this chain and this structure results in a higher molecular weight and a very low vapor pressure. This allows it to easily infiltrate into the groundwater from through the soil and migrate in plumes. It also allows them to be very adsorbable into organic organisms. And because of the saturated structure, with all of the fluorine on there, and because that chemical bond is so strong, it makes them very resistant to oxidation, biodegradation, typical other types of, technology used that would break down other compounds is not successful in breaking these down. So now that we know they're highly prevalent, there have been developing lists of toxicity data, and because they're persistent and bioaccumulative, in 2016, the EPA had set health advisory limits for PFOA and PFOS, and the limit was as a combined, both of those compounds combined to be less than 70 part per trillion, so 70 nanogram per liter. So thinking about that on that scale, if you don't typically work in the nanogram per liter range, it's jarring for how low that number actually is and how small the safe amount of PFAS actually is. So those initial HALs were in review for a long time, and a lot of states actually set lower limits and single-digit advisories or MCLs actually state by state. And this has since evolved to now draft MCLs that would then be a nationally enforceable standard for drinking water. So there are primary standards for many different compounds and chemicals. This would add PFAS to the list. So what actually just came out recently was the list seen below, where PFOA and PFOS are given individual MCL limits of 4 part per trillion. And then 4 other PFAS compounds are grouped together, and they'll be evaluated as a hazard index. And the EPA provides the formula for calculating this number. But the idea is to keep, the overall general concentration of these based on an index below a unitless number of 1. So since this are out, it's a 3-year review period where there's a lot of different testing. We'll see how many and where, and we know it's very prevalent. I think this is going to tell us just how exceptionally prevalent it is. So we've talked about it's out there, it's persistent. The EPA has deemed it as concerning and giving it potential MCLs. So what can we actually do about it? We have a few options. Obviously, our favorite is granular activated carbon, but we do provide anti-exchange resin as well. And then another option for treatment is high pressure membranes, similar to an RO membrane. And there are pros and cons to each of those technologies that we'll kind of discuss here. So obviously, activated carbon and anti-exchange are adsorptive, where they're removing PFAS from the environment and binding it onto the actual adsorbent. RO membranes are processing through and then have PFAS in their rejection water. So they're kind of transferring them from, a dilute state to a concentrated state that can then be disposed of. But that is one of the cons, that you need to dispose of that high concentrated PFAS. So in general, when we're comparing the technologies, it's easiest to compare granulated activated carbon and anion exchange resin because they're both adsorptive. So what's really different about them? Typically, carbon has a lower capital and O&M costs. It's definitely been in use longer for PFAS, and there's probably a lot more information on it, although anion exchange is also pretty well established at this point, and there's a lot of data and information out there on that as well. Depending on the concentration in the compound and everything else, anion exchange resin may be more economical. It's one where we do, if you're comparing the technologies and there's a big driver to look at both, you'd want to look at both. You'd want to actually test. The cons that related to either of them in terms of carbon, high natural organic matter or TOC background, other contaminants can affect the capacity. And because you're looking at such low numbers, nanogram per liter numbers, and TOC, other organics are typically microgram per liter or milligram per liter, you can see some significant effects there. And in terms of the types of compounds, carbon will take out anything. With enough carbon, you can take out pretty much anything. You just need to add a lot more carbon. So that's where the economics kind of take effect when you're comparing the two technologies of really how much carbon does it take. And even the resin is more expensive, it may make more sense to use it in certain applications. There are regenerative applications for resin, but like RO membranes, that then creates a high concentration waste stream that you need to treat. So in the case of all of these, you don't want to create a secondary pollution stream. You want to contain it and get rid of it because it is persistent. You don't want to try to store it again or dispose of it another way. So something that's a disadvantage for both ion exchange resin and RO membranes is that in particular. And I think I've hit the high points there. So if we want to go to the next slide, John. So specifically with PFAS removal, what do all of them have in common? What are differences again between them? Again, because we're trying to target these nanogram per liter, very low level treatment objectives for the application. So again, GAC is the most studied technology, and with, as I said, with enough carbon, we can remove 100% of the contaminants. And given those very, very low levels, and the MCLs at 4 part per trillion or index levels very low, that's where we want to be. And a very good capacity for most PFAS. In addition, they're going to help you overall treat your water. Granular activated carbon's been used for years and years for taste and odor, disinfection byproduct removal, dechlorination. So there are other applications that go along with it as you're getting PFAS removal. A lot of people that have carbon online are seeing they don't have PFAS because the carbon's taking care of that as well as the application it was intended for. Resin is similar. And in addition, like I said, they could have a smaller footprint and the beds are smaller. RO membranes, high pressure membranes, very good rejection rate for PFAS. And again, the main point there is just the high energy input to actually operate them. They're operationally more complex than just a flow through absorption system, and the reject that you have to deal with. Okay, so John will go through some of our activated carbon fundamentals.
Yeah, thanks, Rebecca. So, as we talked about, to understand how activated carbon is effective for PFAS, just want to give some background on how it's used, what it's made from, and show some of the data we have as it relates to removal for PFAS. So as Rebecca mentioned, activated carbon's got over 700 different unique applications. When you wake up in the morning and drink your first cup of coffee or glass of water, right, that's something that's been likely purified with activated carbon. It's similarly used to purify, CO2, or used in a lot of the home air filters that may be implemented at your house or at your workplace. So it's a rather ubiquitous media because of how broad it is and cost effective in removing contaminants. When we talk about activated carbon, it's important to call out that this is, primarily graphite, right? Activated carbon is about 99% graphite. What makes it a little bit different than, graphite that you might think of associated with a pencil lead or something like that is it's a really crude form of graphite, right? Or amorphous. So when we think of, something like pencil lead or pencil graphite, it's a bunch of platelets that are kind of uniform and they kind of slide on top of each other. Activated carbon looks a little bit like a playing deck of cards that's been used by the kids or used for over 20 years, right? It's kind of expanded. There's tears in the deck of cards. There's parts of it that are folded over, and because of that, it makes it even more porous and have a very, very high surface area, which is critical for how it's effective. When we talk about the forces that remove all of these contaminants, activated carbon works through a process known as adsorption. So that's adsorption. Adsorption is something that's often confused with absorptive or absorptive. One, because they kind of sound alike, and two, without kind of a technical understanding, you're basically removing something from something else. So it is a similar mechanism, but there's some very key differences, right? Whenever we talk about adsorption, we're basically adhering something to the surface of an adsorbent or a media. So there's not a subsequent swelling, right? The only thing you will notice is whenever you measure the media before and after, there will be an increase in weight. For instance, whenever we put activated carbon into service for water treatment, whenever you take it out, it's going to be approximately double the weight just because it's got a bunch of water and whatever contaminants it was removing from the stream as well. This is in contrast to an absorptive process, or shown here, the absorptive process, which is really similar to kind of like a sponge, right? Whenever you put it in, it's going to soak up contaminants, water, but there's going to be a subsequent swelling of that media as well. So not only will it weigh more, you'll be increasing in volume as well. Whenever activated carbon, whenever we started presenting on this, I think all the way back in the 60s and 70s, there was a classic example that showed a pie man basically trying to demonstrate the differences between these two processes. Adsorptive processes, basically the man getting hit in the face with the pie, right? There's not a subsequent swelling. He's not ingesting the media. It's mainly adhering to his face. Whereas an absorptive process would be if the man, were basically to ingest the pie, there's essentially a consequence of, the going into the stomach and the stomach swelling. So that's just kind of a classic example trying to explain the differences between those two processes. But the key takeaway is because it's an adsorptive media, activated carbon is essentially pulling molecules or contaminants out of solution in air and holding it very, very tightly to the surface area of the material. It's important to recognize whenever we talk about surface area, it's kind of mind-blowing to think about how much surface area we're actually talking about. Whenever we talk about specifications, it's not uncommon for a gram of activated carbon to have about 1,000 meters squared of surface area. And whenever you do the math, if you put about 5 grams of activated carbon in your hand, that's the equivalent surface area of an entire football field, right? So if you want to think of, it's always Heinz Field to me, but I guess Acrisure Stadium now, right? If you want to think of that field being folded up many, 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 many times until it ultimately fits in a few granules of activated carbon in your hand, that's the amount of surface area we're talking about with this media. Just absolutely mind-blowing amount. And that's important because of basically that's where the contaminants are being held. So the higher the surface area, with the right pore structure and performance, generally the better removal you'll get of various contaminants. So whenever we talk about activated carbon, and I mentioned some of the raw materials in different parts of the world where it's made, it's important to call out there's essentially 4 main raw materials used to make activated carbon. And that's wood, bituminous coal, peat or lignite, which is basically lower, or basically higher ranks of coal, basically closer to the surface, and then coconut as well. And this is essentially the coconut shell part. If you want to, not the meat that you would typically buy in a store, it's kind of the shell part, the brown shell part that typically you'd discard. So these are really the four main sources or raw materials for activated carbon to date. And why that gets to be really important, it may seem, to an untrained eye like it might not matter, but there's really a lot of nuances and a lot of final product characteristics that are inherent in the raw material that is selected. Ash is one component, and ash is basically inorganic material that's present in all activated carbon. That's basically a source of the raw material that's used, which is why we're very selective in the coals or the wood sources that are used for activated carbon manufacturing. Transport pore structure, absorption kinetics is something that is critical to the raw material selection, which we've got some slides later on explaining exactly what that means. Hardness and abrasion is something that's linked to the raw material. So how effective the material is in resisting attrition, right? So you don't want particles rubbing together and essentially breaking down. You want something that's very durable, something that can withstand some of the service load that you would put onto it. So that's linked to the raw materials, which is why these are oftenly used. And essentially when we talk about water treatment, really the bituminous coal and the coconut activated carbons are pretty commonly, most commonly used in certainly the United States and Europe as well. When we talk about the pore structure or the differences between the products, this is what we're talking about on kind of a microscopic level. On a macroscopic level, it's all going to look sort of similar, right? It's black granules. But if you were to look at it basically at 1,000 times magnification, there's some really unique differences between the products that show up in its ultimate performance, right? Whenever we talk about a wood-based activated carbon, you'll see these black lines here are those graphitic platelets we talked about earlier. These little black lines that you see broken off here are dislocations or just small graphitic platelets breaking off from the larger platelet itself. You'll see the wood activated carbon, those platelets are spaced really far apart. You've got a fair amount of distance between them, which causes basically it to have what we call a macroporous structure. So when the contaminant's coming through or being treated with activated carbon, it's kind of got to migrate through this pore structure and then it's held on this surface area here. So this macroscopic or really big pore structures really useful for things like color body removal, which is why wood activated carbons are used predominantly in kind of the wine and food and beverage industry, where decolorization is very, very common. But where it really struggles is if you're trying to remove small things, right? Small contaminants that essentially require a really high pull or a really high force to hold it to those graphitic platelets. Peat and lignite is very similar to the wood-based, basically the wood-based pore structure. It does well in decolorization type applications. What you'll notice here in the lower right-hand corner is the coconut product. It's kind of the exact opposite of the wood or peat or lignite, right? You've got a high concentration of graphitic platelets kind of right next to each other. So if you think of that, kind of like a maze, right? That contaminant trying to navigate through, there's a lot of places for it to kind of sit, but it's pretty hard to get in there, right? So coconut materials aren't always the best for decolorization and aren't always the best for some of these forever chemical removals, just because it's kind of kinetically hindered. It's difficult for that contaminant to navigate through and ultimately reach to an absorption site. You'll notice the bituminous coal-based product in the upper right-hand corner. It's kind of in between all of them, right? It's got a lot of graphitic platelets that are present that can absorb a wide range of contaminants. It's also got a fair amount of space that makes it a little bit easier for the contaminant to navigate through, as well as remove some of the larger color bodies, things like tannins from water as well. So the bituminous coal product is really one that's kind of a jack of all trades, a workhorse product in that it's got very, very broad contaminant removal, whereas a lot of the wood and coconut materials are a little bit more niche or specialized. Whenever we talk about activated carbon, you may have an interest in how it's made. And there's actually a Modern Marvel episode on YouTube for those of you that are interested. But we go through a process known as reagglomeration, where we essentially take a cold blend of material. We pulverize it to about 45 microns in size. In doing that, we then put it through an agglomeration step, which produces a product that's similar to charcoal briquettes that you would see for your grill. We then crush it again to whatever size product we're looking to make. Usually something like a 12 by 40 or 8 by 30 is pretty common in the water treatment industry. We then put it through a baking step, which helps to drive off some VOCs from the product, and then put it through a high temperature activation with steam injection and temperatures reaching about 1800 degrees Fahrenheit to increase the surface area of the product, right? To make that football field size area in 5 grams. This can be in contrast to other methods which are used, which is called direct activation. They start off with kind of a single raw material. They don't go through the pulverization or agglomeration step. They immediately go to crushing, and then the process is pretty similar, right? It goes through the same baking, the same activation, and ultimately producing that finished product or good. You'll see here basically a picture, our Pearl River plant, which is located in Mississippi. This is where we manufacture over 100 million pounds of activated carbon every single year. So pretty remarkable in terms of volume as well. Okay, so to an untrained eye, it may seem kind of counterintuitive. Like, why would you grind it to 45 microns in size just to agglomerate it, just to grind it again? There's some really unique properties that come out of a reagglomerated product that give it strong performance in this PFAS application and others as well. But what you'll see here on the left-hand side is a depiction of a direct activated particle. You can see it's very hard to activate all the way through, because you don't go through this reagglomeration step where you're taking that powder, that 45 micron powder, pushing it back together and reagglomerating it. It's very difficult for the steam and that surface area causing reactions to penetrate all the way through that particle. So you kind of get what they call a clinker, or something that's got basically a low activation center and an over-activated exterior. This is in contrast to that reagglomerated particle, which you can see by the depiction. It's very evenly activated, which helps give it great resistance to breaking down, great attrition resistance, but as well gives it really tailored performance for pore structures that excel for PFAS applications and others as well. So if you take nothing else as it relates to the reagglomeration step, just know that it's a critical process in producing a high performing and consistent product for PFAS applications. Okay. So we talked a little bit about the pore structure. We talked a little bit about the manufacturing method. I now want to just briefly touch on how the mechanism of action for removing contaminants from water, and explain why that manufacturing method matters, why that raw material selection matters. So for something to be removed by activated carbon, there's essentially 4 steps that need to take place. The first is bulk diffusion, right? That contaminant needs to navigate through that bulk carrier, whether it's gas or liquid stream, to get to the carbon granule. Once it gets to the carbon granule, there's a film that forms on the outside, as one would expect in most like pipe flow applications. There's a film that forms there. The contaminant has to navigate through that film. It then goes through a process known as pore diffusion. So it's navigating within that internal porosity of the carbon granule, and then ultimately coming to adsorption, right, which is a surface diffusion reaction where that contaminant's being pulled and adhered to the surface of activated carbon. I like to think of things a little bit more simply, and in terms of an analogy, it's helpful for me sometimes to think of the adsorptive process as kind of like a morning commute right? It takes a wide range of, roads and a whole process to ultimately get to your final destination. Whenever we talk about the reagglomerated coal-based products or navigating through a lot of that internal porosity, it's helpful to think of, these spaces between these particles as kind of man-made highways, right? It allows easy access and quick access to those carbon granules. You can then think of the commute as between those particles as kind of like a two-lane road, right? You got to have pretty equal spacing there. And then ultimately the adsorption process is the car kind of pulling into the parking lot. So whenever we talk about the reagglomerated bituminous coal, it's got a good blend of these highways, two-lane roads, and parking lots, whereas other, raw materials and activated carbon sources are a little bit more specialized. Some have a little bit, more highways, some have a little bit more parking lots, but it's really that balance between the two that creates that high-performing product. As it relates to, activated carbon and how it removes, what it likes, this is just a quick technical graph, but as we move up on the y-axis here, we're essentially increasing in the adsorptive strength of these contaminants within the activated carbon species. So as one could imagine, as you increase, the number of rings, benzene rings, that's something that activated carbon likes very much and will hold very, very closely. Similarly, a double bond's adsorbed better than a single bond, a triple bond better than a double bond. Whenever we look at various kind of organic species, activated carbon really likes iodine. It's actually one of the quality parameters that we use whenever we're comparing activated carbon's quality is how much iodine can it absorb. So if that's on a contaminant, it removes really, really well. You'll notice here the fluorine bond, which Rebecca talked about for PFOA and PFOS, is actually one that negatively impacts how well something can be absorbed, right? It actually prefers the CH bond over that, and that's primarily because of the electronegativity. The fluorine bond is basically the fluorine atom is basically pulling a lot of that electron density, holding it very, very closely, and doesn't want to share it with a lot of the van der Waals interactions with the carbon surface in the adsorptive process. But this is just a handy dandy chart. In the future, if you're ever evaluating activated carbon, it's helpful to know what it likes and what it doesn't for removal. Oh, sorry about that animation there. Okay, Rebecca, you want to cover some of the water and wastewater design considerations?
Sure, and want to touch on these with respect to PFAS and how it relates to system design. What are your really critical process parameters when you're thinking about this? And probably because I have a process development background, that's how I think about it. What's a critical parameter? What's a key parameter? What are you trying to do when you're actually running water through, running vapor through a carbon system, and what's the objective and what's the best way to optimize and to do it? So the design considerations relate to contact time, your flow rate, and the type of adsorber, the type of system that you're going to use. And a lot of these also, relate to any adsorptive media, but the numbers may be different depending on the type or the application. But with respect to PFAS, in general, we'd like to see at least 10 minutes of contact time, and depending on how challenging the compound is or the water matrix, up to 60. And that's really a long time to be processing water through a system, because you need to maintain a sufficient flow rate so that you're dispersing through the activated carbon. It's actually an excellent distributor, but you need to have sufficient velocity so that you're not running down the side of a vessel, or just over pressurizing and seeing too high of a pressure drop to really process efficiently. So within the contact time constraints of 10 to 60 minutes, you want to see about 1 to 8 GPM per foot squared of that surface area. And typical systems are designed to treat between 1 and 1,000 gallons per minute. Not in the same system, obviously, those are different types of design, but that's the range of standard equipment available from Calgon and from many other vendors too. So pictured on the side, the very top black vessel is a 1,000-pound system, and the bottom is a 20,000-pound vessel, actually in multiple of those. So system sizes range for whatever anyone would need to treat between those flow rates. They can operate in parallel, in series, and other things to consider are headspace for allowing to backwash of the carbon. Over time, solids can deposit, organics can deposit different things that cause pressure drops. So you need to be able to backflow through the system to relieve some of that pressure. Anti-siphon loop piping is an important consideration for flow-through type systems. We're operating these in downflow. So in order to ensure that your vessel's flooded through the entire step of the process, you want to make sure your piping on the outlet is elevated enough so that it is above the level of the vessel, so that you maintain a flooded vessel for the whole process, or even during shutdown, you maintain that flooded. So those are kind of our critical parameters. And to go into how they're calculated, what they are, empty bed contact time is a term that's thrown around a lot for carbon vessels, and other types of media as well. But it's really the time that the water is in contact with the GAC for a given bed volume. And it's calculated by looking at your GPM and multiplying by the foot cube per gallon, and then resulting in your foot cube per minute. Then taking your pounds of GAC. So your flow rate divided by your pounds, or your pounds divided by your flow rate gives you your minutes of empty bed contact time. There are two different densities to look at. You have your pack density as you fill a vessel, and then also an expanded after backwashing density. And again, we have the targets of between 10 and 60 minutes, depending on water quality. So almost all drinking water systems are on the low end. It's relatively clean water, and then heavier higher concentration and TOC values in wastewater on the upper ends. Other pre-treatment considerations in the system that can affect the operation would be suspended solids. So we don't want those solids to enter the GAC if it's not going to be adsorbed onto the GAC or onto the adsorptive media. Then we should exclude it upstream. Otherwise, it's really just blocking those adsorptive sites, blocking up your transport structure. Granular activated carbon will act as a very good filter down to about 10 to 15 microns, but it's a very expensive way to filter, and you're excluding your absorption capacity if you're using it in that manner. Metals can also be a problem. Metals tend to deposit onto the carbon, again, creating that fouling layer and blocking off adsorptive sites. Dissolved solids can kind of, we call it cement up the bed, literally turning it into kind of a solid block where you want free-flowing granules. Oils and grease at too high of a concentration are not adsorbed. Any two-phase system is not applicable for treatment. So if it's at a concentration where it's resulting in that two-phase type system, then you'll basically coat the carbon particles and have very inefficient or non-existent adsorption. And biomatter and organisms' biogrowth can also result in fouling. So, keeping a very good water flow, excluding these types of contaminants to allow the carbon to do its job, to really focus on those PFAS or hard to treat contaminants is what we're looking for when we're designing a system. So just another slide on startup, because this is very important, and we do see things go wrong once in a while if these steps aren't followed in a certain way. And carbon's very, forgiving to some extent, but starting up properly can really go a long way to having a long-term, long-running system. We're seeing drinking water systems last for a really long time. We want to keep it that way. We want to make sure everybody's handling the carbon in the proper way and understanding what's important and why these steps are important. So we want to start with, dry carbon then contacting water. All of that carbon has to deaerate, and all of the air has to come out from even those very, very fine adsorptive pores. So the initial soak and wetting of the carbon is really critical to allow it to be fully utilized so that the contaminants can enter those very fine pore structure. So we want to deaerate the bed and then we want to actually backwash the bed because we're providing a range of particle sizes and mesh sizes. So a distribution that has to be segregated so that then subsequent backwashes, you have the same segregation within your bed. And those flow rates are determined by the mesh size and the equipment. But understanding these factors going into an operation can really help, again, create a nice long-term treatment for the system.
Okay. So thanks, Rebecca. I'm going to quickly go through, basically some of the data we have on PFAS treatment, just talk a little bit about our experiences. As Rebecca mentioned, PFAS has been removed with activated carbon for a very long time. It's a well-studied media, and its effectiveness is pretty well studied. We've had over 20 plus years in treating PFAS from drinking water and other sources. We offer basically a range of equipment, activated carbon services, site services to remove the carbon from the vessel, and then a process known as reactivation, where we take the product back, remove the contaminants that are present on it, and then destroy it in a high temperature process similar to the activation process itself. We have over 120 installations for PFAS removal across the country, and those are ranging in various sizes. Anywhere from our smaller units to something up to our Model 14, which I think holds about 60,000 pounds of activated carbon in one of those units alone. So very, very comprehensive as it relates to flow rates and items that we can treat. Whenever we talk about PFAS treatment, it's important to call out we do recommend testing. There's a lot of ways to test activated carbons and its ability to remove contaminants. Isotherms typically aren't recommended for PFAS just because of how low the treatment objectives are. It's very difficult to accurately measure how effective the media is or change out frequencies based on the isotherm testing alone. It's impossible. We do offer bench scale testing, which helps to simulate, basically years of field service in the lab in a matter of weeks or months, which gives you some, real confirmation about change out frequencies, economics, and overall effectiveness for the products. And then piloting systems, another option that can be done, and then ultimately full scale treatment. These are what we call those column scale, lab scale column tests that we run, either RSSCTs or ACTs. What you can see here on the y-axis is basically the concentration of PFAS. On the x-axis, you can see simulated days of operation. And what we're doing here is that we're pumping the solution through that bed of activated carbon and monitoring the effluent or the water that's coming out of the adsorber for PFAS over fixed intervals. Activated carbon's capacity, unfortunately, is not infinite. So you do need to change it out at regular intervals. What we're doing here is monitoring the breakthrough of those contaminants to really understand when that capacity is exhausted and when you might need to change out a bed of carbon. And what you can see here is on the left-hand side is one of those reagglomerated bituminous coal-based products. That's our Filtrazor brand in the US. On the right-hand side is a direct activated coconut. So a little bit different pore structure. Even though the specifications seem somewhat similar. We treated it on a Moon Township, basically tap water source. So you can see very low TOC levels. We had to spike it for PFAS, which is good news. There wasn't PFAS in the water. So we had to spike it at about 200 parts per trillion. And we used various different PFASs. Something from C4 in chain length and PFBA, PFBS, C6s basically with the PFHXA, PFHXS, and then C8, which is the PFOA, PFOS species. And what you can see here on the left-hand side, we had a pretty decent amount of non-detect time for the total PFAS. You can see the PFBA broke through much quicker than a lot of the other PFAS compounds. But if you were to treat, essentially non-detect for, the species that are listed in the MCLs and HALs, you can see a very, very effective bed life for activated carbon, the right activated carbon on the left-hand side. On the right-hand side is that coconut product, and you can see you have rather rapid breakthrough of a lot of the PFAS contaminants that are much better removed with the coal-based material. I'll point out that these were both used at about 10 minutes of empty bed contact time. So we had the same amount of contact time with the material, with the activated carbon material. And this difference of performance is pretty well recognized in the industry. Just that the coconut materials tend to struggle for PFAS removal applications. So key takeaway from this slide is, activated carbon is effective for a wide range of PFAS. As long as you change out the bed at appropriate intervals, you're able to remove to a very, very high degree. And not all activated carbons are created equal. You got to make sure you have the right product for a given application selected. This is just a quick slide. I'll glance over it because I know Rebecca wants to get to reactivation, and we do want to leave some time for questions. A common way to compare medias in the industry is based on bed volumes treated, which you can see here on the x-axis. It's essentially a dimensionless unit, and I know as chemical engineers we love our dimensionless units, but it's really important to compare products as it relates to either days of operation or gallons treated. Whenever you start talking about ion exchange resins or medias that have smaller bed volumes, if you have essentially 2 times the bed volumes through a unit, but the bed is 10 times smaller, you're not treating the same amount of water through that bed that you treat through something that's bigger in terms of empty bed contact times and bed volumes that are present. So if you're ever comparing medias in literature or other, just keep in mind bed volumes is only part of the story. You really have to look at gallons treated or days operation. Okay, Rebecca, I'll turn it over to you for reactivation.
Yeah, and I think we have a few slides, but I'm going to just skip probably more than half of this because we want to get to questions, and we could speak all night about activated carbon and PFAS. So we'll just hit the highlights. Key takeaway: reactivation process, a thermal reactivation process, is not the same as a regeneration process. Reactivation is a high temperature thermal treatment, typically done off-site at a reactivation facility. Regeneration can be performed in process, and typically contaminant remains on the carbon or resin or whatever you're regenerating as part of the process, and you're only getting a portion of that bed life back. With reactivation, we're able to fully reactivate the particle to return it to a virgin-like state. So go ahead to the next slide, John. This is a pictorial of that, showing that after reactivation, the carbon's removed, the spent carbon is now in a virgin-like state, whereas with regeneration, some of that contaminant is going to kind of hang around there. So for PFAS processes in particular, we're not aware of any regenerative processes for GAC. They are in place for ion exchange resin, but again, you have to deal with that extraction solution that's removing the regenerative contaminant, and then deal with the remaining contaminant on the adsorbate. Next slide, please. These are just pictures of furnace types. There's multi-hearth furnace, you see on the left, rotary kiln on the right. They each sort to or serve to move carbon through and then control the atmosphere to impart activation conditions and gasification of the carbon with steam, typically, maybe some carbon dioxide as well. And the carbon should achieve temperatures up to at least 800, almost 1,000 C. This is another, pictogram showing carbon entering an adsorptive process, being used, becoming spent, being removed from that system and transferred and then processed through a furnace for that reactivation treatment, and then put back into service for another application. There's extensive testing required to make sure that you can actually safely handle and safely reactivate that. It's a big part and a big step of that process. And there's a specific department that handles all of these tests and qualification of all the spent media coming back. Next slide. I think we'll skip this one, it's an efficient and sustainable, this is the sustainability point, and one of the points of the topic. So there's a very big CO2 reduction, and advantage to recycling that activated carbon. So we see 80% of the CO2, a reduction of 80% of the CO2 required to produce virgin carbon. With respect to PFAS, it is important to, as I said, not create a secondary pollution stream. So, there's a lot of academic literature going on and academic research showing PFAS destruction at reactivation temperatures in conjunction with GAC. So this is noted here. University of North Dakota has some very good literature out there for reference. Next slide. We'll highlight our own literature as well. Calgon has a peer review paper looking at thermal destruction through a full-scale reactivation furnace using a PFAS-laden spent. That was published last September, and it's open access in the Remediation Journal. And just very high level, what was demonstrated was greater than 99.99% destruction of targeted PFAS up to 35 compound list, and greater than 99.999 of PFOA, PFOS, Gen X, and PFBS that were the current HALs at that time. So thank you. I think we have a few minutes for questions. Appreciate everyone's time.
All right. Thank you, John, and thank you, Rebecca. And now we open for questions. You can submit your question through chat or just unmute yourself and talk. Someone's asking, will the slide be shared?
Yeah, they can be. If you have an interest or want to understand more, feel free to reach out to us. But yeah, we can share the slides.
All right. Thank you.
Mm-hmm. No problem.
Okay, we have a question that can active carbon destroy all 4,700 compounds in the PFAS class?
Well, the analytical is up to 70. When we did our research, it was at 36. Now they're up to 70. So we'll see how it progresses in terms of how they can quantify and measure it. Our process is only as good as what we can measure using the best available analytical.
Yeah, I think EPA has a research program is dedicated to develop analytical methods for all the compounds.
It'll be interesting to see how that area evolves over the next 5 to 10 years.
Yeah. Any other questions? Do we have any other questions? Is there a way to determine the limit of pollutants absorbed to the gas used in this system?
So if I'm understanding the question correctly, I just went through there, but so activated carbon's kind of interesting in the sense that it doesn't really care what you're trying to remove or what levels you're trying to remove. It's going to absorb everything it can until its capacity is exhausted. So it's really difficult to put limit of pollutants absorbed onto the GAC. What we typically see is if you operate in lead lag, if you operate and design your system effectively, you can do things like slipstreams, where you may not necessarily have to remove all of the contaminants or species. You can kind of design it out such that you can sort of have limits and kind of tailor that solution. But as it relates to the technology itself, it's kind of agnostic and will absorb everything it can until it no longer can.
Okay, next questions. Are these PFAS removal methods you describe only used for water? Can it be used for anything else? Air emissions?
Yeah. So it's and it's one of the reasons why our slides had like liquid and vapor in some of them, right? Like activated carbon can be used to purify a whole range of solutions, a whole range of vapor phase streams. It's not just limited to water itself. That there may be some impact, right? Like if you're trying to treat, like a propane or a hydrocarbon stream, that's something that activated carbon, as one could imagine, likes a great deal. But it still can remove, contaminants from it as well.
All right. Our last question, do you apply different reactivation procedures for different gas types?
I think the only thing to note there would be batch versus continuous and segregated versus pool reactivation. So in some cases, a customer wants their exact carbon returned to the service for their application. And that could be for anything really. So that's going to be run as a batch process versus when we take wastewater from many, many different customers, they're all treating wastewater and it's all going to go back to treat wastewater after reactivation. That's done as a continuous process, and the product's a pool react that can be used, anywhere for anyone's wastewater. So it's application, but in terms of the temperatures, really target those high temperatures. We want to be at activation temperature. So they're not really manipulated very much at all.
Yeah.
All right. I guess with that, we conclude today's lecture. And thank you very much, John and Rebecca, and the excellent talk. And thank you everyone for joining tonight's lecture. Thank you and have a good night.
Thanks for putting this on, Ron Kong. Appreciate it.
All right. Bye-bye.
Thank you, Ron.
Bye-bye.
Bye. Thanks, everyone.